Welcome to Brain Vision.
For this problem on the topic of conservation of energy, we are told that a car of a given mass accelerates from rest as the driver presses the gas pedal. Now, we know a function for the acceleration with respect to time that is given for the first few seconds of motion. Now, t is in seconds for this expression and a is in meters per square second. So we have the acceleration a is 1.16 t minus 0.21 t squared plus 0.24 t cubed. We want to calculate in this problem the change in kinetic energy of the car during the interval from 0 to 2.5 seconds, the minimum average power output of the engine over this time interval, and we want to know why the value in part B is described as the minimum value. Now, to calculate the change in kinetic energy, we have to integrate the expression for the acceleration as a function of time to obtain the car's velocity. So the velocity v is the integral over time from 0 to t of the acceleration dt. So this is the integral from 0 to t, and we'll substitute our expression for the acceleration, which is 1.16 t minus 0.21 t squared plus 0.24 t cubed. So this is with respect to dt. So if we integrate this over time, we get this to be 1.16 times t squared over 2 minus 0.21 times t cubed over 3 plus 0.24 t to the power 4 over 4, and we'll evaluate this from the time t is equal to 0 to t is equal to t. So this simplifies into an expression for the velocity with respect to time. So v of t is 0.58 t squared minus 0.07 t cubed plus 0.06 t to the power 4. So now we have an expression for v as a function of t. Now we can see that at t is equal to 0, the velocity is equal to 0. So the initial velocity is 0, and hence the car starts from rest. Now, the velocity at 2.5 seconds, we'll call it Vf, is 0.58, and that's meters per cubic second times the time of 2.5 seconds all squared minus 0.07 meters per second to the fourth times the time 2.5 second all cubed plus the final term of 0.06 meters per second to the 5 times the time 2.5 seconds all to the power 4, which gives us the final velocity after 2.5 seconds to be 4.88 meters per second. So now we have the initial velocity at t is equal to 0, which is 0, and the velocity at t is equal to 2.5, which is 4.88 meters per second. So the change in kinetic energy during this interval is therefore the initial kinetic energy plus the non-conservative work done is equal to the final kinetic energy. So Ki plus W is equal to Kf. So from here we can calculate the change in kinetic energy. So that's 0, which is the initial kinetic energy, plus the work done is equal to the final kinetic energy, a half mVf squared. And so this is equal to a half times the mass of 1,160 kg times the speed 4.88 meters per second all squared, which gives us the change in kinetic energy during this interval to be 1.38 times 10 to the power 4 joules. So that's the total change in kinetic energy, and hence the total work done by the car in this process. Now in part B, we want to calculate the minimum average power output of the engine over this time interval. Now the road does work on the car when the engine turns the wheels and the car moves. So the engine and the road together transform chemical potential energy in the gasoline into kinetic energy of the car. So the power, we know, is the work done per unit time, so W divided by delta T. The work done is the same as the kinetic energy change, which we calculated above to be 1.38 times 10 to the 4 joules. And this work happens in a time of 2.5 seconds. So the average power output is 5.52 times 10 to the power 3 watts. Now, lastly, for part C, we want to know why the value in part B is described as the minimum value. And the answer to this is that the value in B represents only energy that leaves the engine and is transformed to kinetic energy of the car. We also have additional energy that leaves the engine by sound and heat, and even more that leaves as the engine has to do work against frictional forces and air resistance.